So in this video, we'll be talking about fatigue. Fatigue damage is among the major issues in engineering because it increases with the number of applied loading cycles in a cumulative manner and can lead to fracture and failure of the considered part. So here are some a brief history regarding fatigue. Beginning in the first half of the 19th century, mechanical failure were observed to take place in metals and materials subject to repetitive stress well below the yield strength. Below the yield strength. And the theory came to be that the metal became tired or fatigued, and hence the term fatigue or metal fatigue. So how can we define fatigue? Fatigue by definition is a form of failure that occurs in structure that is subjected to a fluctuating stress. Fluctuating stress. And among the key points to understand fatigue is that it can be defined as a form of failure that occurs in structures subjected to dynamic and fluctuating stress. It can cause a part failure, responsible for about 90% of a mechanical engineering failure. In addition to that, it occurs suddenly and without warning, and brittle in nature, even in ductile materials. So, for example, you imagine a bridge, a jembatan, with a cars driving repeatedly over it. So a number of cars in any given day might differ. So one thing about fatigue that you have to remember that that parts or that material can fail even though the maximum stress the part is subjected to is much less than the yield stress. So we can say that fatigue is forces equals to Fd, where any forces that we applied over time will cause crack growth that will further promote premature failure. So how does fatigue start? So usually we start with some kind of a crack initiation. This can start by a tiny micro crack or the way the material was arranged, etc. In some point, we need a site for this crack to start to grow, and as our load varies over time, that crack is going to get bigger and bigger with each cycle. And eventually, this will proceed to a brittle style of fracture, and this could even happen for a ductile material. Something like aluminium could suddenly fail with no warning. That is typical for ductile materials such as a lot of deformation. We know that a ductile material will exhibit a lot of deformation before failure. And so we can say that there are three stages that involve in fatigue failure. And the first step is where the crack formation occurs. Second stage is where the growth occurs, and finally, the third stage is when the fracture occurs. So here are some important fundamentals if you want to understand more about fatigue. First, terminology is fatigue itself. Fatigue can be defined as the lowering of strength or failure of a material due to repetitive stress, which may be above or below the yield strength. And secondly, we have a creep. We'll be discussing more about creep later. Creep can be defined as a time-dependent permanent deformation at a high temperature occurring at a constant loading or constant stress. And you also need to know about SN curve, or also known as a Wöhler curve, that can be defined as a graph that's showing a stress as a function of a number of cycles in fatigue. Then we have a beach or a clamshell marks that can be defined as a pattern often seen on a component subjected to fatigue, like what we can see in the figure here. And here we have the origin of fracture, and we have a beach mark or clamshell marks. And you also need to know about rotating cantilever beam testing. This is a technique used for fatigue testing. Rotating beam fatigue testers are one of the oldest methods used to determine the material's fatigue behavior. So we already know that fatigue is a failure mechanism, that involve the cracking or fracturing of materials that are structural components and structural components due to a cyclic or a fluctuating stress. And while we applied a stress maybe in form of tensile or compressive or torsional, crack initiation and propagation are due to the tensile component. One of the interesting facts about fatigue development is that, like what I have mentioned several times before, is that fatigue cracks can be initiated and propagated well below the yield strength of the material. And how does fatigue failure looks like? Actually, a fatigue failure is quite easy to identify, like what we can see in the figure here. The fracture surface, particularly near the origin, is typically smooth. And this fatigue crack always initiate at the surface at the stress concentration points, such as surface defect, sharp surface features, etc. And the surface becomes rougher as the original crack increase in size and may be fibrous during the final crack propagation. And here is an example of a schematic representation of a steel shaft. We can see that the failure initiated at this point. And from here we can see at the catastrophic zone here, it no longer supports any loading. And there are several factors that may influence the fatigue strength. Among the factors are the range of stress, the geometry of the component, the material properties itself, and finally, environmental factors such as thermal and corrosive condition. So a fatigue failure occurs under a dynamic loading, condition, and the crack propagation progress with each loading cycle. And this slow crack propagation is often undetected until the final catastrophic failure happens in the industrial component. So a crack initiation at the sites of the stress concentration, such as microcracks, scratches, indents, interior corners, dislocation, slip snaps, etc. And hence, the quality of the surface is important if you want to avoid fatigue from propagating. So as we can see in the figure here, it shows the step that involve in a crack propagation. As we can see in the first stage, is where the initial slow propagation involve, and we can see that along the crystal plane with a high resolve shear stress, the crack propagation occurred. It involves just a few grain, and it has a flat fracture surface. And when it proceeds to stage 2, faster propagation perpendicular to the applied stress occurred. Crack grows by repetitive blunting. And a sharpening process at the crack tip, producing a rough surface. And finally, crack eventually reaches a critical dimension and will propagate very rapidly. So we already know how fatigue happens in materials. A load of insufficient magnitude to cause failure in a single application may lead to a failure if it is removed and reapplied repeatedly. So what I want all of you to do is you do your own reading, find ways how can we avoid fatigue from happening. You can refer to any related books or from any sources available online. Okay, that's all for today, and see you again.